Hi everyone, I am Laurice Angeles, third year BS Chemistry student, and I am from UP Materials Science Society. In this Chem 31 review video, we will be answering and discussing some practice questions and problems on alkenes and cycloalkenes. Before we start, let us first quickly recall that alkenes and cycloalkenes are hydrocarbons with carbon-carbon double bonds. They are called hydrocarbons because from the name itself, again, they are composed exclusively of carbons and hydrogen. They are also called unsaturated carbons because their carbons have less hydrogens bonded to them compared to alkenes, which we tackled in another review video. Also, alkenes are open carbon chains, while cycloalkenes are cyclic carbon chains. Okay, let's start. Predict the product of the following hydrohalogenation reaction of one pentene and show its mechanism. You may pause the video first to answer on your own. We have here a reaction between 1-pentene and hydrobromic acid. We know that the general reaction for typical electrophilic addition in alkenes is this. Where E stands for electrophiles and Nu for nucleophiles. We also know that hydrohalogenation reactions with bromine involved are highly regioselective, and so we will have a major product. From this, we can say that the major product of the reaction above is 2-bromopentene. Now, for its mechanism, let us recall that the double bond here in 1-pentene is nucleophilic or electron-rich, and so it would be attacked by electrophiles such as our hydrogen here in hydrobromic acid. Then the bond between hydrogen and bromine here will break, leaving us with either a secondary carbocation or primary carbocation, depending on where the hydrogen will attack. But again, we know that a secondary carbocation is more stable, and so we will go with this one instead of the primary carbocation. Also, we will have a bromide ion as another product. Now, bromine, being highly regioselective, will choose to attack this secondary carbocation, leaving us with this product. In this reaction, we can see that a carbocation is the intermediate. Now, as mentioned above, different types of carbocations have relative stabilities, and it follows the sequence. The most stable is the tertiary carbocation. Less stable than that is the secondary carbocation. And less stable than that is the primary carbocation. And the least stable is the methyl carbocation. Now, when a carbocation is less stable, it can choose to undergo rearrangement to be more stable if its structure will allow it to. We have two ways of carbocation rearrangement. First is the alkyl shift, and second is the hydrogen or hydride shift. For methyl shift, this is what happens. So this is our carbocation. The R represents an alkyl group. It can shift to the other carbon if that will yield a more stable carbocation. An example of an alkyl shift is when we have this carbocation. We can see that this carbocation is a secondary carbocation because the positive charge is on the secondary carbon. A more stable carbocation than a secondary one is a tertiary carbocation. Observing this compound, we can see that if we will shift this alkyl group to the secondary carbon, we can have a more stable tertiary carbocation. For hydride shift, it is very similar to alkyl shift, but instead of an alkyl group doing the shift, it will be a hydrogen atom. So this is our carbocation. This hydrogen atom can shift to the other carbon if that will yield a more stable carbocation, like this one. For an example, let's have this carbocation. We can see again that this carbocation is a secondary one because the positive charge is on the secondary carbon. A more stable carbocation than this is a tertiary one, and we can have that if the hydrogen atom will shift from the tertiary carbon to the secondary one. And there. We have now a more stable tertiary carbocation through hydride shift. Let's have more examples of hydrohalogenation reactions of alkenes. Predict the product of the following hydrohalogenation reactions. You may pause the video if you want to answer first on your own. For number 1, we have 3-methyl, 1-butene reacting with hydrobromic acid. So we know that the double bond will be attacked by hydrogen and the bond will break between hydrogen and bromine, giving us a secondary carbocation right here. We chose a secondary carbocation over a primary one because it is more stable. And then of course, we also have the bromide ion. Next step here should be the bromide ion attacking the carbocation. But wait, we see here that this carbocation could potentially be more stable by shifting into a tertiary carbocation through hydride shift. And so, considering that hydride shift, we end up with a tertiary carbocation right here. Now, the bromide ion now can attack the carbocation and you will have 2-bromo, 2-methylbutane as the major product. For number 2, we have here a vinyl cyclopentane reacting with a hydrobromic acid. Again, you may pause the video if you wish to answer this problem on your own first. First, we know that the hydrogen will attack the double bond here, and the bond between the hydrogen and bromine will break, and so we will have this secondary carbocation, which is more stable than the primary carbocation na mapoproduce if kukunin natin yung hydrogen from here sa primary. Again, notice that we have a tertiary carbon present in this secondary carbocation, meaning we can possibly have a more stable tertiary carbocation through hydride shift again. And so you will be having this carbocation result. Now, let's consider both of these carbocations. For this one, the bromide ion will attack here and will yield this product. While for this carbocation, the bromide ion will attack here and will yield this product. Between these two products, syempre, the major product is this one because this one came from the more stable carbocation. Let's move on to more examples. This one is a simple exercise on the reduction of alkenes. Arrange the following alkenes in order of decreasing heat of hydrogenation and stability. You may pause the video if you want to answer the items first on your own. Okay, the heat of hydrogenation is the quantity of heat evolved or released when 1 mole of an alkene is hydrogenated. And the higher the heat of hydrogenation is, the more unstable the alkene. And in that case, we have the following order for the stability of alkenes based on their heats of hydrogenation. This alkene with 4 alkyl groups is the most stable, and the less and less alkyl groups attached, the alkene becomes less stable. And so from here, we can see that the greater the number of alkyl groups attached directly to the double bonded carbon, the more stable the alkene is. This is what we call the Saint-Zeph rule. So according nga sa Saint-Zeph rule, ang pinakamaraming alkyl groups yung pinaka-stable. And from these alkenes, that is alkene C. Since that is the most stable one, we can put that here sa answer natin sa letter B as the most stable alkene. So we will just look for the next alkene na may pinakamaraming alkyl groups and so on. So the next is alkene E with 3 methyl groups. So the next one could either be D or B, but transalkenes are more stable than cisalkenes. And so since B is the transalkene, we will put it first and then C. And then lastly, we have alkene A as the least stable one with 1 ethyl or alkyl group. Now, in answering letter A, order of decreasing heat of hydrogenation, we can just invert the order in our answer here sa letter B. Kasi nga, we recall that as heat of hydrogenation increases, stability decreases. So, baliktad lang talaga yan. So, for A, we have A, D, B, E, C as our decreasing order. Fill in the corresponding alkenes in the blanks in the reactions provided below. You may pause the video to answer them on your own. The following reactions are called ozonolysis. It is a vigorous oxidation reaction that affects a cleavage or binibreak niya yung carbon-carbon double bond of the alkenes. And here is the general reaction. We have here the alkene, and then reacted with ozone, from which the name of the reaction came, and zinc, water, and hydrogen ion. So simply, it just breaks the double bond and the alkene turns into aldehydes and ketones. So both the products can either be both aldehydes or both ketones, or an aldehyde and a ketone. An aldehyde has this general form. Again, the R here represents an alkyl group. And this ketone has this general form. Answering number 1, we can see that the products are both aldehydes. We can rewrite them this way. There, and looking at the general reaction of ozonolysis, all we have to do to figure out the alkene here is to connect the aldehyde groups together and form an alkene. So you have the carbon-carbon double bond here from this carbon and this carbon, and we will just copy the remaining alkyl groups. Rewriting this compound in condensed form, this is what it looks like. CH3, CH2, CH2, CH, double bond, CH, CH2, CH3. And this is called 3-heptene. For number 2, we will repeat the same process. But as you can see, this one is just one product with a ketone and aldehyde group. But don't worry, still all we have to do is to connect these two functional groups together to form an alkene. We can rewrite this one in bond line form. And then we will first draw the double bond and copy the remaining alkyl group. And this one will go around and meet the other side of the double bond. And there you have it, you have the alkene, which is actually a cycloalkene. For number 3, we will again repeat the process. We will first draw the double bond and copy the remaining alkyl groups like this. And that is your final answer. Predict the products of the following Alkadine reactions and show their mechanisms. So this is just number 1. You may pause the video to answer on your own first. So we have here a penta-1,3-diene reacted with hydrochloric acid. And this alkadiene here is a conjugated diene, meaning this will be an electrophilic addition reaction yielding 1,2 addition and 1,4 addition products. What does that mean? Ibig sabihin, this electrophile will attack this nucleophile right here and yield this carbocation, which is in resonance with this carbocation. If you have questions or clarifications on resonance structures, feel free to message our Facebook page or comment them in this video. Moving on, the chloride ion will attack this carbocation and will yield this product. While in here, the chloride ion will attack this carbocation and will yield this product. Since chloride is not as highly selective as bromide, these products are equally abundant. There's no major product. This is your 1,2 addition product, while this is the 1,4 addition product. And that is your final answer. For number 2, we have a 1,3-butadiene reacted with hydrochloric acid, or HCl. Again, you may pause the video if you wish to answer this first on your own. So, we are going to go through the same mechanism as in number 1. This hydrogen will attack this double bond to produce this carbocation. Again, which is also in resonance with this carbocation. Again, we have here resonance structures. For this, the chloride ion will attack here and will yield this product, 1,2 addition product. And for this, the chloride ion will attack here and will yield this 1,4 addition product. And there you have your final answers. And that is the end of this review video. If you have any questions or clarifications on this video or anything about Chem 31, just comment them in this video and I will try my best to address them as soon as possible before your exam on Monday. And also, feel free to message our Facebook page, which is UP Materials Science Society. And also, if you have the time, please answer the feedback form linked in the description of this video so that we will know what and where should we improve on in these review videos, or so that we will find out what type of review you'd want next time sa second long exam nyo. I hope you learned something and I wish you good luck on your exam. Thank you and goodbye.